All right, folks, we are essentially done with Unit 5, chemical bonding, but I thought it was important that we go back and make certain that we understand all the concepts with the challenge question. We're going to be taking a look at a question from the 2014 AP examination, because if we can do that, we can do just about anything. So let's, before we start though, take a look at one last definition. I want to take a look at something called a dipole moment. What do we mean by dipole moment? Well, let's break this down. What do we mean by dipole, first of all? Well, when we say dipole, what we mean is something that has two different ends, two ends that are different. Let's relate this to something that we know. So, for example, we live on the planet Earth, and we know that the Earth rotates on an axis, right? It rotates around an axis. And that there's a North Pole, right? And there's a South Pole, and they're not the same. For those of you who are still believers, Santa Claus lives on the North Pole, right? He doesn't live at the South Pole. So they're different. The North Pole and the South Pole are different. Well, how do we relate that to chemical terms? What does dipole mean in a chemical sense? Well, let's take a look at a chemical compound that we're very familiar with, and that's CO2. Let me draw the Lewis structure for carbon dioxide. So that's it, just like that. So CO2 has that structure right there. Now, I want to take a look at each of the bonds, right? I want to take a look at the bond on the left, the carbon-oxygen bond on this left-hand side, right-hand side, I'm sorry. And we know that from our studies of electronegativity that oxygen is more electronegative than is carbon, right? It's higher and further up and to the right on the periodic table. So that means that the electronegativity arrow is going to go this way. It's going to go towards the right, just like that, right? It's going to go that way. But what about the other side? Well, the other side, as it turns out, is identical, is it not? Because however electronegative oxygen is, and I don't know the exact number, don't need to know, but I do know that whatever it is the same on the right as the left. So that means that the electronegativity arrow, once again, is going to point in the opposite direction, just like that. It's going to point that way and to the left, right? So right and left are going to be identical. When the right and the left are exactly the same, or for the entire molecule, when everything is exactly the same, we say that there is no dipole moment. Okay? There's no dipole moment. Now, that means that the molecule is symmetrical in every way. The molecule is symmetrical in every way. But let's do this. Let's change something. Let's, for example, say, let's say we have carbon, double bond oxygen on the left, just like we always had. But look what's going to happen on the right. I'm going to make a substitution. I'm going to substitute sulfur for oxygen. And in doing so, I'm not going to change the bond polarity, because look, if you look at the bond polarity on the left, obviously it's the same, right, as before. So the arrow goes in that direction. But on the right-hand side, sulfur is still more electronegative than is carbon. So the arrow goes this way as well, just like that. But still, it's not balanced. Sulfur has a different electronegativity than is oxygen. Now, I can put an electronegativity sign on the sulfur. It is more electronegative than is the carbon, but still, the electronegativity difference on either side is not the same. It's not the same. And because of that, what we say is that there is a dipole moment. There is a dipole moment for this second one, right? All right, now let's do this. Let's take a look at a molecule that we're extremely familiar with and determine whether or not it has a dipole moment. That's this molecule right here, and it shouldn't come as a big shock that this is water, right? Just like that. Remember that it is a bent molecule, right? It's a bent molecule. So if I look at this bond right here between hydrogen and oxygen, that hydrogen-oxygen bond is polar. The electronegativity arrow goes in that direction, right? Oxygen is obviously more electronegative than is hydrogen. This electronegativity arrow goes in this direction, just like that. The two electronegativity arrows in magnitude are identical, right? They're the same. Oxygen, hydrogen is the same thing. But they're both pointed in roughly the same direction. Not exactly the same direction, but roughly the same direction. One's up and to the right, one's up and to the left, but they're both up. Nothing is bouncing back down. So once again, we say that this molecule has a dipole moment, right? It's not entirely balanced. It's not entirely balanced. Okay, now that's dipole moment. Now let's take a look at a question from the 2014 AP chemistry examination. If we can answer this, then we're going to be in good shape. All right. So it says two possible geometric shapes for the ClF3 molecule are trigonal planar and T-shaped. Trigonal planar and T-shaped. Now the student does some research and learns that the molecule has a dipole moment. The molecule has a dipole moment. It says which of the two shapes is consistent with the fact that the ClF3 molecule has a dipole moment. Justify your answer in terms of bond polarity and molecular structure. Folks, I want you to pause the video now, and I want you to take some time to try to answer this question on your own, right? Try to answer this on your own. I'll get back to you in a minute, and we'll compare answers. See you in there. All right, hopefully you've had a chance to formulate your answer. And let me read the question one more time, because I think it's important that we really understand what is happening here. All right, it says two possible geometric shapes for the ClF3 molecule are trigonal planar and T-shaped. So that's going to be important for us. Trigonal planar and T-shaped, just like that, right? Now, let me push that way just a little bit. Okay, there we go. The student does some research and learns the molecule has a dipole moment. They do research. They learn that the molecule has a dipole moment. We know what dipole moment means now. Which of the two shapes is consistent with the fact the ClF3 molecule has a dipole moment? Okay? Justify your answer in terms of bond polarity and molecular structure. So we have to discuss in our answer bond polarity and molecular structure. So hopefully, you've had a chance to take a look at this question and apply what you know about molecular geometry, bond polarity, and dipole moments. So let's compare answers. Now, let me just tell you that when I wrote my answer, I kind of separated my scratch paper from what I wanted the grader to see. So what you see on the left in this area here is my scratch, the drawings that I've made just to convince myself of the answer. And so what I determined from my drawings was this. I drew, first of all, the trigonal planar structure in the upper left-hand corner right here. We have ClF, F, F, just like that. And I drew the electronegativity arrows. I know that the electronegativity of fluorine is 4.0. I don't need to know that. I just need to know it's more than chlorine. And I need to know that they're all the same. So if this was F, and this is F, and this is F, then those arrows are going to balance each other out. What does that mean? That means that there is no dipole moment for this structure. No dipole moment for the trigonal planar structure. But let's compare that then to the T-shaped structure. All right? The T-shaped structure is this one here. Cl, F, 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 just like that. Now the arrow to the left and the arrow to the right are going to balance each other out. They're going to cancel, no problem. But look at this F going down. The fluorine going down is not balanced with another fluorine going up, or anything else going up for that matter. And that means that there is a dipole moment. There is a dipole moment for this bottom structure here. So now in my mind, I am convinced that the answer is that it is a T-shaped structure, right? It is a T-shaped structure and not a non-polar, or excuse me, not a trigonal planar molecule. So let me now write my answer. This is what I've written. Compare it to what you wrote. The T-shaped molecule is the correct shape for the ClF3 in question. So I want to make the grader recognize, I don't want to be kind of fuzzy on my answer. I want to know this is what I've picked. The T-shaped molecule is the correct shape for the ClF3 in question. The geometry of the ClF3 in the trigonal planar configuration is a non-polar, and I put in parentheses, no dipole moment, and not consistent with the student's research findings. Notice how I put the word research in because they use the word research. So I write the geometry of the ClF3 in the trigonal planar configuration, that's this one on the top, is a non-polar, no dipole moment, and not consistent with the student's research findings. Then I go on to write, although each of the bonds in the T-shaped molecule is polar. Notice how I'm careful. I had outlined or written in my answer, or in the reading of the question, I had highlighted the word bond polarity. So I want to make sure that I mention bond polarity in my answer. It says, although each of the bonds in the T-shaped molecule is polar, they do not cancel each other out. The T-shaped molecule has a dipole moment. So that's kind of a restatement of my initial answer. So let me read the question again to make absolutely sure that I've answered everything that I need to answer. And by the way, I put this as scratch for my own edification so that I would understand what the correct answer is, but I would definitely include that in my answer to the grader. All right, so here we go. It says two possible geometric shapes for the ClF3 molecule are trigonal planar and T-shape. Got that. The student does some research and learns that the molecule has a dipole moment. All right. Which of the two shapes is consistent with the fact that the ClF3 molecule has a dipole moment? Justify your answer in terms of bond polarity and molecular structure. Okay. So in my answer, I've certainly addressed those two issues. I've talked about the bond polarity, how the bonds were all polar, but they didn't cancel each other out in the T-shaped molecule. And therefore, that was going to be the answer since the student's research indicated that there was a dipole moment. Folks, that'll do it for Unit 5, Chemical Bonding. I'll see you in the next unit. Thanks. Bye-bye.